Imagine pressing the pause button on the entire universe, not for 1 second, not 1 trillionth of a second, not even a billionth of a second. Imagine stopping time at the smallest instant nature may possibly allow. Now, ask yourself something even stranger. If time can be divided into smaller and smaller pieces, what lies between two of those smallest pieces? Is there another tiny moment hidden inside? Does time continue forever, becoming smaller without end? Or does reality simply refuse to answer the question? This sounds like a puzzle, but it has become one of the deepest questions in modern physics. Because the closer scientists look at reality, the more they begin to suspect that time may not flow the way it feels. Right now, your heart is beating. Your eyes are moving. The Earth is spinning. The universe appears to be changing continuously. Everything seems smooth, like watching a river flowing. But appearances can be misleading. A movie looks smooth too, yet every film is actually made from separate frames. Play them quickly enough, and your brain creates continuous motion. For more than 2,000 years, scientists and philosophers wondered whether reality itself might be built from unimaginably tiny moments. Or is time truly continuous? Modern physics has no final answer. And surprisingly, our best theories disagree with each other. One of them treats time as perfectly smooth. The other hints that smoothness might disappear when we look closely enough. Somewhere between these two pictures, our understanding of the universe breaks completely. That breaking point has a name: the Planck scale. It is so small that ordinary imagination becomes useless. Numbers stop making sense. Language begins to fail, and mathematics itself starts warning us that we may be asking questions it cannot yet answer. The Planck time is approximately 5.39 times 10 to the minus 44 seconds. Written as a decimal, it begins with 43 zeros before the first meaningful digit appears. It is such a tiny interval that light, the fastest thing in the universe, travels only 1 Planck length during that interval, less than 2 times 10 to the minus 35 meters. A distance so incredibly small that an atom were expanded to the size of the observable universe, a Planck length would still be far smaller than the atom originally was. These numbers are difficult to picture, but the numbers themselves are not the real mystery. The mystery is why they exist at all. Nobody discovered the Planck time by measuring a tiny clock. It emerged from mathematics. In 1899, the German physicist Max Planck noticed something remarkable. Nature contains several fundamental constants: the speed of light, the gravitational constant, and the constant that now carries his own name, Planck's constant. These numbers appear everywhere in physics. They do not depend on humans. They do not depend on planets or galaxies. They seem woven into reality itself. When Planck combined these constants in just the right way, they produced natural units. A natural unit of length, a natural unit of mass, a natural unit of energy, and a natural unit of time. It was as though nature had quietly hidden its own measuring system inside the laws of physics. At first, these units seemed like mathematical curiosities. Interesting, but perhaps not physically important. More than a century later, physicists began realizing they might represent something profound. Because every time we push our theories toward the Planck scale, those theories stop agreeing with each other. General relativity, Einstein's masterpiece, describes gravity as the curvature of space-time itself. Mass bends space. Space tells matter how to move. The theory has passed every experimental test thrown at it. It predicts black holes, gravitational waves, the expansion of the universe, even tiny corrections in the GPS satellites guiding your phone every day. On large scales, it works beautifully. Quantum mechanics is equally successful. It describes atoms, electrons, light, chemical reactions, lasers, semiconductors. Nearly every piece of modern technology depends on it. Its predictions have been confirmed to astonishing precision. Some calculations agree with experiments to more than 10 decimal places. No scientific theory has ever been tested so accurately. So we possess two extraordinary descriptions of nature, each almost unbelievably successful, each repeatedly confirmed. Yet they refuse to fit together. Imagine owning two maps. One perfectly describes every road in your country. The other perfectly describes every street inside every city. Separately, they never fail. But the moment you try placing one on top of the other, nothing matches. Roads disappear, cities shift, directions contradict each other. That is the situation modern physics faces today. General relativity assumes spacetime is smooth, continuous, like perfectly calm fabric. Quantum mechanics assumes uncertainty exists everywhere. Nothing can possess perfectly definite values simultaneously. When gravity becomes extremely strong and quantum effects become extremely important, both theories demand control at the same time. Instead, both begin producing impossible answers: infinite energies, meaningless equations, broken mathematics. It happens at astonishing places: inside black holes, at the beginning of the universe, and around the Planck time. This is why the Planck time matters, not because anyone has proven time is divided into tiny pieces, but because our current understanding cannot see beyond it. It is less like a brick wall and more like the edge of an unfinished map. Beyond that edge, our equations become unreliable. Imagine hiking through mountains with a beautifully detailed map. Roads, rivers, villages, everything is clearly marked. Then suddenly, the paper ends. Not because the mountains end, only because nobody has mapped them yet. The Planck time may be exactly that, the point where our mathematical map simply stops. This distinction is important. Many people say the Planck time is the smallest possible moment. Modern physics does not actually know that. What physicists can honestly say is something slightly different. Our present theories lose predictive power near this scale. Whether time truly becomes discrete, or remains continuous, or disappears entirely, is still unknown. Already our original question begins changing. Instead of asking, what happens between two Planck times, we may first need to ask, does the phrase between two Planck times even have meaning? That sounds like philosophy, yet it emerges directly from physics. Suppose someone asked, what is north of the North Pole? At first, it sounds like a sensible question, but after thinking for a moment, you realize the question itself breaks down. The concept of north no longer applies. Some physicists suspect the Planck time may create a similar boundary, not necessarily a physical limit, a conceptual one, a place where everyday language no longer matches reality. Our brains evolved to understand apples falling from trees, water flowing downhill, clouds moving across the sky. Nothing in human evolution prepared us to think about intervals lasting 5 × 10⁻44 seconds. So we borrow familiar words: moments, duration, before, after, between. Yet these words may quietly fail us. Einstein himself transformed our understanding of time more than a century ago. Before relativity, most scientists believed time flowed identically everywhere. A universal cosmic clock ticked across the universe. Every observer shared the same now. Relativity shattered that idea. Two observers moving differently can disagree about how much time passes. Clocks moving quickly tick more slowly. Gravity itself changes the flow of time. Near a massive object, time runs differently than it does far away. This is no longer theory. Atomic clocks have measured it directly. Even climbing a mountain changes how quickly time passes by an unimaginably tiny amount. Time already
is stranger than everyday experience suggests, and quantum physics would soon make it stranger still. Because once scientists entered the microscopic world, they discovered something deeply unsettling. The equations describing quantum particles hardly seem to care which direction time moves. Many of the fundamental laws work almost equally well whether time moves forward or backward. Yet your everyday experience clearly has a direction.
You remember yesterday, not tomorrow. A glass falls and shatters. The pieces never spontaneously leap back together. Smoke spreads across a room. It never gathers neatly back into a candle. Somewhere, the universe chooses an arrow of time. But where does that arrow come from? And if time itself begins to lose meaning near the Planck scale, what becomes of that arrow? Perhaps, before asking what exists between two Planck times, we first need to understand whether time itself is truly fundamental, or whether, like temperature or color, it emerges from something even deeper. Temperature feels fundamental: hot, cold, warm. It seems like a basic property of the universe. But imagine shrinking yourself until you become smaller than a single atom. You would never find temperature hiding inside. You would find atoms moving, some moving slowly, some moving rapidly. Temperature is simply a way of describing the average motion of countless particles. It emerges from something deeper. Could time be similar? Could the smooth flow you experience every day be nothing more than an average description of an underlying microscopic reality? Many physicists believe this possibility deserves serious attention, not because it has been proven, but because it naturally appears when our best theories reach their limits. To understand why, we need to look at something that almost everyone takes for granted: the ticking of a clock. Every clock measures change. A pendulum swings, a quartz crystal vibrates, an atom changes between energy levels. Even the most accurate atomic clocks are simply counting repeated physical events. Without change, there is no clock. Without clocks, how would we even know time is passing? This question sounds philosophical, yet it has become a real problem in theoretical physics. Suppose the entire universe froze perfectly. Every atom, every photon, every field. Nothing moved, nothing changed. Would time still pass? Or would the very idea of time become meaningless? Some physicists argue that without change, time has no physical meaning at all. Others believe time exists independently, even if nothing happens. The debate continues today. Already, our simple picture of time is beginning to crack. We usually imagine time as a long road. Every moment follows the previous one: past, present, future, one after another. But nature never actually gives us this road. What nature gives us are events. A radioactive atom decays. A photon is emitted. An electron changes energy. One event influences another. Perhaps reality is built from relationships between events, not from a giant invisible clock ticking in the background. This idea becomes surprisingly important when we approach the Planck scale, because at extremely tiny distances and unimaginably short times, ordinary ideas about space and time begin colliding with quantum uncertainty. Quantum uncertainty is often misunderstood. People sometimes say quantum mechanics means everything is random. That is not quite true. The uncertainty principle, discovered by Werner Heisenberg, is much more specific. It tells us there are certain pairs of quantities that cannot both be known with unlimited precision at the same time. The most famous pair is position and momentum. If you determine the exact position of a particle, its momentum becomes increasingly uncertain. If you know its momentum perfectly, its exact position becomes impossible to define. This is not because our instruments are poor. It is built into nature itself. No improvement in technology can remove it. Now imagine trying to measure an incredibly tiny interval of time.
How would you do it? Perhaps by using an incredibly energetic particle. A shorter wavelength lets us examine smaller scales. That sounds reasonable. But here another strange rule appears. According to quantum physics, shorter wavelengths require higher energy. The smaller the distance we wish to investigate, the greater the energy we must concentrate into that region. For ordinary experiments, this causes no problem. Particle accelerators do exactly this.
The Large Hadron Collider pushes particles to enormous energies before smashing them together. From these collisions, scientists learn about the fundamental structure of matter. But suppose we continue increasing the energy. Higher, higher still, closer and closer to the Planck scale. Eventually, gravity refuses to stay quiet. According to Einstein's general relativity, energy itself produces gravity, not just mass. Energy also curves spacetime. So if we squeeze enough energy into an incredibly tiny region, that region begins bending spacetime dramatically. Keep increasing the energy, and something astonishing happens. Instead of revealing smaller details, the energy creates a microscopic black hole. The very tool we hoped would reveal reality now hides it. Imagine shining an increasingly brighter flashlight into a cave. Normally, brighter light reveals more detail. But eventually, the flashlight becomes so powerful that it melts the cave entrance shut. You can no longer see inside. Something similar seems to happen near the Planck scale. Our attempt to observe smaller distances may destroy the very information we hoped to uncover. This remarkable idea appears in several different approaches to quantum gravity. Although the details differ, they point toward the same conclusion. Nature may contain a fundamental observational limit, not because reality ends, but because observation itself changes reality too dramatically. This is one reason physicists take the Planck scale so seriously. It is not simply another small number. It marks the place where gravity and quantum mechanics become equally important. Neither theory can safely ignore the other anymore. Unfortunately, we still do not possess a complete theory that combines them. For decades, scientists have searched for one. Many candidates have appeared, each elegant, each fascinating, each incomplete. One of the oldest ideas is called quantum gravity. The goal sounds simple: treat gravity the same way we treat the other fundamental forces. Electromagnetism has photons, the strong nuclear force has gluons, the weak force has W and Z bosons. Perhaps gravity also has a quantum particle. Physicists call this hypothetical particle the graviton. If gravitons exist, they would carry the gravitational interaction across space, just as photons carry electromagnetic forces. Yet no experiment has ever detected one. Not because scientists forgot to look, because gravity is unbelievably weak compared with the other forces. A tiny refrigerator magnet easily overcomes the gravitational pull of our entire planet on a paperclip. That weakness makes individual gravitons almost impossible to observe with present technology. Even if gravitons exist, they may not solve our deepest problem. When physicists try applying ordinary quantum methods to gravity, the mathematics quickly becomes unstable. Infinite quantities appear everywhere. Predictions lose meaning. Something essential is missing. This has encouraged many researchers to ask a more radical question. What if gravity is not the thing that must be quantized? What if space and time themselves are not fundamental? Imagine standing close to a television screen. From only a few centimeters away, the picture disappears. You notice tiny glowing pixels. Red, green, blue. The smooth image was only an illusion created by countless smaller pieces. Now step back. The pixels vanish. A beautiful landscape appears. Perhaps spacetime works similarly. From our enormous human perspective, it appears perfectly smooth. But zoom inward far enough, and perhaps an entirely different microscopic structure emerges. If that picture is correct,
then asking what happens between two Planck times could resemble asking what lies between two pixels on a digital screen. The answer would not be another smaller pixel. The answer might simply be nothing. Not empty space, not hidden moments, because the question itself assumes continuity where none exists. Of course, this remains speculation. No experiment has yet confirmed that time is built from discrete units. Some theories predict discreteness. Others predict continuity. Nature has not yet revealed which path she chose. And then, there's an even stranger possibility. Perhaps time is neither continuous nor discrete. Perhaps it is not fundamental at all. Perhaps time emerges from something completely timeless. That sounds impossible. How could a timeless reality produce a universe where clocks tick, stars evolve, and people grow older? Yet one of the most famous equations in quantum gravity quietly points in exactly that direction. An equation so strange that when physicists first encountered it, they could hardly believe what it was telling them. One of the most surprising discoveries in modern physics is not something that scientists found. It is something they lost. Time. Not in experiments, not in observations, but inside one of the deepest equations ever written. Imagine spending years trying to combine Einstein's theory of gravity with quantum mechanics. Thousands of pages of mathematics, decades of research. Finally, an equation begins to emerge. You expect it to describe the evolution of the entire universe. You expect time to appear everywhere. After all, every equation in physics seems to need it. Velocity changes with time. Energy changes with time. Particles move through time. Everything depends on time. But then, you look at the final equation, and time is gone. Completely gone. This is known as the Wheeler-DeWitt equation, developed in the 1960s by physicists John Archibald Wheeler and Bryce DeWitt. Unlike Schrödinger's equation, which tells us how a quantum system changes over time, the Wheeler-DeWitt equation describes the quantum state of the entire universe. And astonishingly, there is no time variable in it. It simply does not appear. This has become known as the problem of time. It is one of the greatest unsolved problems in theoretical physics, because if our deepest equation describing the universe contains no time, where does the time you experience every second actually come from? Is it hidden somewhere inside the mathematics? Did physicists accidentally remove it? Or has time never been fundamental at all? This is where our everyday intuition becomes almost useless. We instinctively imagine the universe as a sequence, one moment, then another, like beads on a string. But the Wheeler-DeWitt equation suggests a completely different possibility. The universe may simply exist as one enormous quantum state. No universal clock, no master timeline, no invisible second hand sweeping across reality. Just relationships, patterns, possibilities. The flow of time might emerge only when small parts of this timeless universe begin interacting with one another. Think about a book. Every page already exists. The first page, the middle, the last. The story itself does not move. Only the reader experiences the story one page at a time. Could reality work like that? Could the universe exist as a complete structure, while conscious observers experience only one tiny slice after another? This idea is not established fact, but it is taken seriously enough that physicists continue exploring it today. Notice how different this is from asking whether time is made of tiny pieces. Now we are asking something much deeper. What if time itself is only an emergent phenomenon, just as temperature emerges from moving atoms? If that were true, then asking, what happens between two Planck times, would resemble asking, what happens between two temperatures? The question would no longer make physical sense.
because temperature is not a fundamental ingredient. It is a description of deeper microscopic behavior. Perhaps Planck time is similar. Perhaps it marks the scale where our familiar concept of time stops being useful because something more fundamental takes over. But if time is not fundamental, what is? This question has inspired several radically different ideas. One of the most fascinating comes from loop quantum gravity. Instead of treating space-time as a perfectly smooth fabric, this approach suggests that geometry itself is quantized, not just matter, not just light, space itself. Imagine zooming into a digital photograph. At first, it appears perfectly smooth. Mountains, clouds, faces. Everything looks continuous. Keep enlarging it. Eventually, individual pixels appear. The smooth picture was never truly smooth. Your eyes simply could not resolve its tiny structure. Loop quantum gravity proposes something similar for the universe. At incredibly small scales, space may consist of tiny quantum building blocks connected together like an immense network. These networks are called spin networks. The name can be misleading. They are not little spinning objects. They are mathematical structures describing discrete chunks of geometry. According to this picture, areas and volumes may come only in specific quantum amounts, not any value whatsoever. Just as an atom cannot possess every possible energy, space itself may not possess every possible size. If that is correct, distance is no longer infinitely divisible. Neither is volume. And naturally, many physicists wonder whether time might also possess a similar microscopic structure. Interestingly, loop quantum gravity does not simply place tiny cubes inside empty space. The network is the space. There is no separate background waiting underneath. Geometry is built from relationships between these quantum elements. In other words, space is not the stage upon which physics happens. The stage itself is part of the performance. That idea is incredibly difficult to accept because every human experience tells us space already exists before objects occupy it. Yet Einstein had already begun weakening that assumption. General relativity taught us that space-time bends, expands, ripples. It behaves dynamically rather than acting as a fixed background. Loop quantum gravity pushes this one step further. Perhaps there is no smooth background at all, only quantum geometry. If so, what becomes of time? Here, the picture grows even stranger. In many versions of the theory, time is not represented by a universal flowing river. Instead, change occurs through transitions between different quantum geometries. There is no external cosmic clock keeping count, only the evolution of relationships. This is a profound shift in perspective. Instead of saying time causes change, the theory almost suggests change creates the appearance of time. That reversal sounds subtle, but it completely changes how we think about reality. Because if change is fundamental and time merely describes ordered change, then the Planck time may not be a tiny duration that nature waits between events. It may simply be the scale at which our ordinary language about duration begins to fail. Yet even this may not be the deepest possibility. Some physicists argue that neither space nor time is fundamental. Both may emerge together from something even more abstract. Not particles, not fields, not geometry, but information itself. If that idea sounds unbelievable, the next chapter of this mystery becomes even stranger, because several modern theories suggest that reality may be woven together not by matter, but by information and quantum entanglement. One reason physicists believe something extraordinary happens near the Planck time is not because they have measured it. It is because two of the most successful theories ever created begin making incompatible demands on reality. To understand this conflict, we have to stop thinking about particles. Instead, we must think about space-time itself. In Einstein's general relativity, space-time is not merely an empty stage where events occur. It is a physical object. It bends, it stretches, it carries gravitational waves, it expands with the universe. Most importantly, its geometry is determined by energy and momentum. Einstein summarized this relationship in a remarkably compact equation. The left side describes the curvature of spacetime. The right side describes the matter and energy inside it. Matter tells spacetime how to curve. Curved spacetime tells matter how to move. For more than a century, every precision test has confirmed this picture. But there is a hidden assumption inside Einstein's theory that is rarely discussed. Spacetime is assumed to be a smooth, differentiable manifold. In mathematics, that means no matter how much you zoom in, you can always zoom further. Every point has neighboring points. Every curve can be made arbitrarily smooth. There is no smallest distance, no smallest duration. General relativity is built upon continuity. Quantum mechanics is built upon something very different. It says physical quantities fluctuate. Even a perfect vacuum cannot remain perfectly quiet. Every quantum field possesses unavoidable zero-point fluctuations. These are not measurement errors, they are consequences of the uncertainty principle itself. Now imagine applying those fluctuations not to electrons, not to photons, but to spacetime itself. If gravity is quantum, then spacetime itself should fluctuate, not occasionally, continuously. At everyday scales, these fluctuations would be unimaginably tiny, far too small to notice. But as we approach the Planck length, their magnitude becomes comparable to the geometry itself. The smooth fabric of spacetime begins to lose its meaning. John Wheeler gave this bizarre regime a memorable name. He called it quantum foam. The name is poetic, but the physics behind it is profound. Imagine looking at the ocean from an airplane. The surface appears calm and smooth. Descend lower, small waves appear. Closer still, foam, spray, chaotic turbulence. The smooth surface never disappeared. It was only an approximation valid from far away. Wheeler suggested spacetime behaves similarly. At macroscopic scales, it appears smooth enough for Einstein's equations to work beautifully. But near the Planck scale, the geometry itself may become violently turbulent. Tiny regions may continually curve, reconnect, and fluctuate because of quantum uncertainty. It's important to be careful here. Quantum foam is not an experimentally observed fact. It is a theoretical expectation that naturally arises when one tries to combine quantum mechanics with gravity. Many candidate theories predict similar behavior, but the exact microscopic structure remains unknown. Still, the implications are astonishing, because once spacetime itself fluctuates, the very concepts of distance and duration become uncertain. Suppose you wanted to measure exactly one Planck length. You would normally imagine placing 2 points in space and measuring the distance between them. But what if those points are no longer fixed? What if spacetime itself is fluctuating while you measure it? Then the ruler changes while making the measurement. The distance is no longer well defined. Now apply the same reasoning to time. Suppose you ask, what happens between 2 Planck times? That question assumes there exists a perfectly defined interval separating one instant from another. But if spacetime itself possesses quantum uncertainty, the interval itself may fluctuate. The separation between moments is no longer an absolute quantity. This is a much deeper problem than simply saying time becomes discrete. It suggests that below some scale, the very distinction between before and after may lose operational meaning. Physicists sometimes express this idea another way. They ask not what exists, but what can, even in principle, be measured. Modern physics is built upon operational definitions. A physical quantity has meaning only if there exists some conceivable experiment capable of measuring it. This philosophy became especially important after Einstein's work on relativity. The speed of light, simultaneity, distance, time,
all acquire meaning through measurement procedures. Now imagine trying to construct a clock capable of resolving intervals much smaller than the Planck time. The clock must respond extraordinarily quickly. According to quantum mechanics, that requires enormous energy. But according to general relativity, that concentration of energy curves spacetime. Increase the energy enough, and the clock itself collapses into a microscopic black hole. The device disappears behind its own event horizon before completing the measurement. Notice what has happened.
The limitation is no longer technological, it is physical. Nature appears to prevent the measurement itself. This argument was independently explored by several researchers, including Mead in the 1960s, and later expanded in studies of quantum gravity. The conclusion is subtle. Physics does not currently prove that intervals shorter than the Planck time do not exist. Instead, it suggests that such intervals may be fundamentally unobservable. And in physics, the distinction matters enormously. There is another fascinating clue. Every known quantum field theory assumes particles interact on a background spacetime whose geometry is already given. Even when particles appear and disappear, the stage remains fixed. Gravity refuses to cooperate with this picture, because gravity is the geometry. Trying to quantize gravity, therefore, means trying to quantize the stage itself. Imagine writing a play where the actors continuously change the shape of the theater while performing. The seats move, the walls bend, the floor stretches. The stage cannot be separated from the actors anymore. This is precisely why gravity is fundamentally different from every other force. Electromagnetism acts within spacetime. Gravity defines spacetime itself. This distinction lies at the heart of the quantum gravity problem, and it hints that our entire framework for thinking about time may need to be replaced. Perhaps time is not another coordinate waiting to be measured. Perhaps it emerges from the collective behavior of something much deeper. Something whose true variables are not seconds or meters, but quantum relationships that do not resemble space or time at all. If that is true, then the Planck time is not the smallest tick of the universe's clock. It is the point where the very idea of a cosmic clock begins to dissolve. At this point, a natural question appears. If time begins to lose its meaning, why don't we notice it? Why does the world around us appear so smooth? Why doesn't reality flicker or jump or reveal tiny quantum grains of time? The answer may lie in a phenomenon that appears throughout physics: emergence. A single water molecule does not have a wave. A single molecule simply moves according to the laws of mechanics. A wave appears only when billions upon billions of molecules begin moving together. The wave is real. You can surf on it. It can knock down a ship. But it is not fundamental. It emerges from collective behavior. Temperature emerges. Pressure emerges. Sound emerges. Even rigidity emerges. A diamond feels perfectly solid, yet more than 99.99999999999999999% of every atom inside it is empty space. Its strength comes from electromagnetic interactions between quantum particles. The solidity is real, but it is not fundamental. Some physicists suspect space-time itself belongs in this same category. Perhaps what we call space and what we call time are large-scale phenomena, perfectly real, but not fundamental. If that idea is correct, then asking what happens between two Planck times may be like asking what lies between two temperatures. The question quietly assumes that temperature is a microscopic ingredient. It is not. The microscopic ingredients are molecules. Temperature is the language we use after averaging over an enormous number of microscopic states. This brings us to one of the most exciting developments in modern theoretical physics: the possibility that space-time emerges from quantum entanglement. Entanglement is often introduced as a mysterious connection between distant particles. While that description is useful, it hides something much deeper. Entanglement is not simply a curious quantum effect. Many physicists now believe it may be the very fabric from which spacetime is woven. To understand why, we first need to rethink what information means in physics.
Imagine two quantum particles prepared in a single shared quantum state. You separate them 1 meter, then 1,000 kilometers, then opposite sides of the galaxy. Their spatial separation grows enormously, but mathematically, their quantum state remains a single object. The distance between them grows.
Their quantum relationship does not. Already, something extraordinary has happened. Geometry says the particles are far apart. Quantum mechanics says they are described by one inseparable wave function. Which description is more fundamental? For decades, this question seemed philosophical. Then, researchers began noticing remarkable mathematical connections. In 1997, theoretical physicist Juan Maldacena proposed one of the most influential ideas in modern physics. Known as the ADS-CFT correspondence, it showed that two seemingly different theories could describe exactly the same physics. One theory contains gravity in a higher dimensional spacetime. The other contains no gravity at all and lives on its lower dimensional boundary. At first, this looked like an extraordinary mathematical coincidence. But over the following years, physicists realized something astonishing. The geometry of the gravitational spacetime appears to be encoded in patterns of quantum entanglement within the boundary theory. In simple words, change the entanglement, and you change the geometry. Space itself seems to respond to quantum information. This was an unexpected result. For centuries, scientists imagined matter existing inside space. Now, mathematics suggested the opposite. The structure of space might emerge from relationships between quantum states. In 2006, physicists Shinsei Ryu and Tadashi Takayanagi discovered an elegant formula connecting entanglement entropy with the area of geometric surfaces inside spacetime. Again, geometry and information appeared inseparable. Then, in 2013, theorists Juan Maldacena and Leonard Susskind proposed an even more provocative idea. They suggested a relationship summarized by the phrase ER equals EPR. At first glance, those four letters mean almost nothing. Yet they combine two of the deepest concepts in modern physics. EPR refers to quantum entanglement, first discussed by Albert Einstein, Boris Podolsky, and Nathan Rose in 1935. ER refers to the Einstein-Rose bridge, better known as a wormhole. The proposal was breathtaking. Perhaps every entangled system is connected by an extremely subtle geometric bridge. Not a tunnel that spacecraft can fly through, not a science fiction shortcut. A mathematical connection suggesting that entanglement and space-time geometry are two descriptions of the same underlying reality. This idea remains speculative. No experiment has confirmed ER equals EPR. But it has profoundly influenced research into quantum gravity because it hints at something extraordinary. Maybe space-time is not fundamental. Maybe geometry grows out of entanglement. If so, our original question changes once again. Not what happens between two Planck times. Instead, what microscopic process gives rise to the experience of time at all? Some researchers now believe the answer may not involve clocks, or durations, or flowing moments. It may involve the continual rearrangement of quantum information. Think about a movie stored on a hard drive. The entire film exists simultaneously as patterns of information. There is no past frame or future frame inside the storage device, only data. Time appears only when the information is read sequentially. Perhaps the universe behaves similarly. Not literally like a computer, that analogy quickly breaks down. But perhaps temporal order emerges only when quantum information evolves in certain structured ways. If that is true, then asking what exists between two Planck times is like asking what exists between two frames before the projector has even started. For more than a century, physicists have searched for the smallest moment in nature. Not because they wanted another tiny number, but because they believed that somewhere, at the very edge of reality, the universe might finally reveal how it truly works. Instead, the closer they came, the stranger everything became. The Planck time did not become another milestone on a timeline. It became the place where the timeline itself began to disappear. Our equations continued working beautifully, until they didn't. General relativity continued describing smooth spacetime, until quantum uncertainty became impossible to ignore. Quantum mechanics continued describing microscopic reality, until gravity refused to stay in the background. Neither theory failed because it was wrong. Each failed because it was incomplete. They were trying to describe the same universe using two different languages. Some researchers believe time is made from tiny quantum transitions. Others believe it emerges from quantum entanglement. Some argue that only relationships between events are real. Others think the universe exists as a timeless quantum state, and what we call now is simply our experience of moving through it. There is no agreement, and perhaps that is exactly what makes this question so remarkable. For thousands of years, people believed time was the simplest thing imaginable, something so obvious that it needed no explanation. Today, many physicists suspect it may be the most mysterious feature of reality, not because it moves strangely, but because it may not move at all. Think again about the question we asked at the very beginning. What happens between two Planck times? At first, it sounded like a question waiting for a number. Now it sounds completely different, because after everything we have explored, we no longer know whether there is a between. If time is continuous, there may be infinitely many moments. If time is quantized, there may be none. If time emerges, the question itself may only exist at our scale of reality. And if time is an illusion, then perhaps neither Planck times, nor seconds, nor centuries are the true language of the universe. Perhaps beneath everything we experience, beneath clocks, beneath gravity, beneath quantum fields, beneath even space-time itself, there exists a deeper reality, one that has never experienced a single second, a reality where nothing flows, nothing waits, nothing ages. Only relationships exist, only information, only possibility. The remarkable part is that this is no longer only philosophy. Every year, new mathematical models, new quantum experiments, and new ideas about gravity continue pushing us toward this hidden layer of reality. The answers remain incomplete, but one thing has become surprisingly clear. The closer science comes to understanding the universe, the less certain it becomes that time is part of its foundation. Perhaps future physicists will discover that the Planck time truly is the smallest possible tick of nature. Perhaps they will discover that time emerges from quantum information. Or perhaps they will find that the universe never needed time to exist in the first place. Until then, the space between two Planck times remains one of the few places where mathematics grows quiet, experiments cannot yet follow, and imagination must wait for evidence. Sometimes the deepest discoveries are not the answers we find. They are the questions that refuse to disappear. And perhaps this question has been quietly waiting since the very first moment that we began calling time. If time is not fundamental, then something else must be. Physics never removes an idea unless it replaces it with something deeper. Newton's gravity was not simply discarded. Einstein explained it as an approximation of curved spacetime. Classical mechanics was not destroyed by quantum mechanics. It emerged as a special case when quantum effects become extremely small. Every revolution in physics has followed the same pattern. The old picture still works, but only within certain limits. Perhaps our everyday experience of time is another approximation, accurate for human life, accurate for planets, accurate for galaxies, but incomplete at the smallest scales. This raises another remarkable possibility. Maybe the universe does not evolve through moments. Maybe it evolves through events. At first glance, moments and events sound almost identical. But in physics, they are very different ideas. A moment is something we imagine existing everywhere. We picture an invisible slice cutting across the entire universe. Everything that exists right now belongs to that slice. This feels obvious, yet Einstein showed it cannot be true. Two observers moving relative to one another do not agree on what now means. An event, however, is different. An event is local. A photon strikes an atom. An electron changes energy. A star explodes. An event simply happens. It does not require a universal present shared by the entire cosmos. This distinction inspired one of the most intriguing approaches to quantum gravity. It is known as causal set theory. Instead of assuming the universe is made from space, this theory begins with something much simpler: events. Nothing else. No smooth spacetime. No invisible cosmic grid. Only individual events connected by cause and effect. Imagine looking at a constellation. At first, you notice stars scattered across the sky. Then your mind begins connecting them into familiar shapes: the Great Bear, Orion, Cassiopeia. The shapes were never physically drawn. They emerged from relationships between individual points. Causal set theory asks whether spacetime itself could emerge in the same way. Perhaps reality is not a smooth fabric at all. Perhaps it is an enormous network of causally connected events. Each event knows only one thing: which events could have influenced it, and which events it can influence. From this immense web, distance may emerge, geometry may emerge, even time itself may emerge. If this picture is correct, there is no hidden clock ticking beneath reality, only an ever-growing structure of causal relationships. Now return to our original question: what happens between two Planck times? According to this viewpoint, perhaps nothing exists between them, because there are no tiny moments waiting to be filled. There are only events. The universe does not advance by ticking, it advances by happening. Notice how different this is from our everyday intuition. We imagine time flowing while things occur inside it. Causal set theory quietly reverses the logic. Things occur, and what we call time is simply the ordering of those occurrences. Whether this idea is correct remains unknown, but remarkably, it preserves one important feature: cause always comes before effect. Not because time forces it, but because causality itself becomes fundamental. This emphasis on relationships appears again and again throughout modern theoretical physics. Different theories begin with different mathematics, different assumptions, different goals. Yet many of them gradually move away from viewing space-time as fundamental. Instead, they build reality from connections, relationships, information, or quantum states. This convergence is one reason many physicists believe we are moving towards something profound. Not because the theories agree, they do not, but because they repeatedly point away from smooth space-time as the ultimate foundation. Then another astonishing proposal appeared, one that sounds almost impossible the first time you hear it. Suppose the entire universe is timeless. Not mostly timeless, completely timeless. How could anyone inside such a universe ever experience time passing? At first, the idea seems self-contradictory. If there is no time, nothing can change. If nothing changes, nothing can happen. Yet, in the early 1980s, physicists Don Page and William Wooters proposed an elegant mechanism suggesting that this intuition may be wrong. Imagine the universe as one enormous quantum state. From the outside, nothing evolves.
The complete quantum state simply exists. There is no external clock measuring its evolution. Now divide the universe into two parts. One part becomes a clock, the other part becomes the system being observed. Neither possesses an independent flow of time. Instead, their quantum entanglement creates correlations. When the clock appears to change, the other system changes with it. Neither one is moving through an external time. They are simply correlated. From inside the universe, an observer naturally interprets these changing correlations as the passage of time. In other words, time is not supplied from outside. It emerges from the internal relationships between quantum systems. This idea is called the Page-Wouters mechanism. It remained largely theoretical for decades. Then something remarkable happened. In 2013, experimental physicists created simplified quantum systems demonstrating the basic principle. The experiments did not prove that our universe works this way, but they show that the mathematics is physically consistent. A timeless quantum state can contain observers who experience temporal evolution internally. Think carefully about what this means. The universe may not need an external clock. It may not even need a universal now. The experience of time could arise entirely from quantum correlations between parts of the universe itself. This changes our original question once again. Perhaps asking, what happens between two Planck times, is like asking, what happens between two pages of a book? The answer depends entirely on whether you are reading the book or looking at the complete book all at once. For the reader, events unfold sequentially. For the book, every page already exists. Physics has not yet decided which picture better describes reality. Perhaps neither is correct. Perhaps both are incomplete. But what makes this so extraordinary is that these ideas are no longer philosophical thought experiments alone. They arise naturally from the mathematics of quantum gravity, and they force us to confront a possibility that would have sounded absurd only a century ago. The universe may not contain a master clock anywhere, not inside atoms, not inside black holes, not beyond the edge of the observable universe. Perhaps the ticking we experience every second is something the universe creates, rather than something it fundamentally possesses. Something remarkable begins to happen when we place all of these theories side by side. At first, they seem completely different. Loop quantum gravity speaks about quantum geometry. Causal set theory speaks about events. The Page-Wouters mechanism speaks about quantum entanglement. General relativity speaks about curved spacetime. Quantum field theory speaks about fields filling the universe. String theory speaks about vibrating strings existing in more dimensions than we can directly observe. Each theory has its own mathematics, its own assumptions, its own language. Yet beneath all these differences, a pattern quietly begins to emerge. Almost none of them treat time the way we experience it. Instead, time keeps losing its privileged position. Sometimes it becomes an approximation, sometimes a relationship, sometimes a consequence of entropy, sometimes it disappears entirely from the equations.
This convergence is difficult to ignore. Physicists disagree on almost everything. Yet many of their deepest theories seem to agree on one surprising possibility. Time may not sit at the bottom of reality. Perhaps it is built from something even more fundamental. That idea forces us to ask an uncomfortable question. Have we been thinking about reality backwards all along? For thousands of years, humans naturally assumed that the universe was built like a theater. First, there is space. Then, time begins to flow. Finally, matter enters the stage and starts moving. Modern physics keeps reversing that picture. Quantum field theory tells us particles are not fundamental objects. They are excitations of fields. General relativity tells us gravity is not a force pulling through space. It is the geometry of space-time itself. Quantum gravity hints that space-time itself may not be fundamental either. One layer after another, the foundation keeps disappearing. Every time physicists believe they have reached the bottom,
another deeper layer appears. It's almost like peeling an onion, except instead of finding a solid center, the layers become increasingly abstract. Particles become fields. Fields become quantum states. Geometry becomes information. Time becomes relationships. The closer we approach the Planck scale, the less reality resembles anything our senses evolved to understand. This should not surprise us. Human intuition evolved on the African savanna, not inside black holes, not inside particle accelerators, not at 10 to the minus 44 seconds. Our brains were designed to throw stones accurately, to recognize faces, to survive. They were never designed to understand the microscopic architecture of spacetime. Perhaps that is why every great revolution in physics has felt impossible at first. The Earth moves, time slows, mass becomes energy. Particles behave like waves. Empty space contains energy. Black holes evaporate. Each idea sounded absurd until nature repeatedly confirmed it. So we should be careful. The fact that something sounds impossible has never been reliable evidence against it. There is another clue that often goes unnoticed. Every successful physical theory has removed something humans once believed was absolute. Aristotle believed rest was absolute. Newton showed that only motion matters. Newton believed time was absolute. Einstein showed that time depends on the observer. Einstein believed space-time formed the continuous arena of reality. Quantum gravity now asks whether even space-time is only approximate. The history of physics has been a history of removing absolutes, one by one.
Our certainties disappear. Perhaps time is simply the next certainty waiting to fall. If that happens, then the Planck time may never become the smallest tick of nature. Instead, future physicists may discover that the Planck scale marks the boundary between two completely different descriptions of reality. Above it, space and time exist. Below it, they do not. Just as water stops behaving like a continuous fluid when viewed molecule by molecule, space-time may stop behaving like space-time when viewed at the Planck scale. Not because reality ends, because our familiar concepts no longer apply. Think again about the original question. What happens between two Planck times? At the beginning of this journey, it sounded like a missing interval, a tiny gap waiting to be explored. Now, after following modern physics to its limits, the question has transformed. It no longer asks about a tiny duration, it asks whether duration itself exists at the deepest level. That is a much stranger question, because it suggests that every clock, every heartbeat, every orbit around the sun, every memory you possess, may all be describing something that is not fundamentally there. Not an illusion, an emergent reality. Just as a rainbow is real, even though no single droplet contains a rainbow. Just as a wave is real, even though no single water molecule contains a wave, time may be real without being fundamental. And if that is true, then somewhere beneath the flow of seconds, beneath the ticking of atomic clocks, beneath the birth of stars, beneath the expansion of the universe itself, there may exist a level of reality where nothing ever flows, nothing ever waits, nothing ever becomes older. Only an intricate web of quantum relationships existing all at once. Perhaps that is why every attempt to look beyond the Planck time has failed. Not because the universe is hiding something from us, but because we keep asking the question in the language of time, when the answer may belong to a reality that has never known time at all.